All right, so electrons in atoms and the periodic table. So we'll talk about a lot of trends here also. So you might be familiar with the Hindenburg. It was a large blimp, and instead of using helium like we use for like party balloons, they used hydrogen for this blimp. And something went wrong. I think actually in watching a documentary, it was a thermite reaction because they had rust on like the big balloon part and then aluminum in the paint, and it reacted and then set the whole thing on fire. But you know, hydrogen and helium aren't that different on the periodic table, right? Like hydrogen's got 1 proton, helium's got 2. Hydrogen doesn't have any neutrons, helium generally has 2 neutrons. So what is it that makes these two so different? Why is hydrogen reactive, whereas helium is completely inert? All right, and that's why modern blimps, although there are a few of them, are filled with helium.
So what you're saying is the F movie F.
Uh-huh.
Legit?
Oh yeah, well, on that subject, that's where David Blaine did that stunt, where he like held onto a bunch of balloons and then floated up, and he wanted to fly up higher than Mount Everest, but they ended up cutting him off because they thought he might be getting like, well, he was oxygen deprived a little bit. So,
You can actually do that.
yeah, you need a lot of balloons. You could do that. Yeah, so it's a good thing they used helium and not hydrogen. So we talked about these group or reactivity on the periodic table a little bit, I think. So our group 1 elements, lithium, sodium, potassium, those are all also very reactive. And even as we move farther into the periodic table, like group 2, those are reactive but a little bit less reactive. And so a big part of this chapter is talking about why these trends exist. And also the other noble gases under helium are all also inert. They don't react with anything. So we're going to talk about 2 models, and mostly want you to just remember the specific differences between those 2 models. There will be a question about it on the next exam. The Bohr model and the quantum mechanical model, and they propose explanations for the inertness of helium and the reactivity of hydrogen and the periodic law. And they're kind of a window into the past of chemistry, into like before we had supercomputers and microscopes and all the fancy instrumentation to figure out what's actually going on inside of an atom, and how the scientists back then tried to hypothesize about what makes atoms tick. And they explain, especially the quantum mechanical model, explains a lot of the chemical and physical properties of the elements, and lets us predict properties of other elements. Quantum mechanics is weird. If you've watched Marvel movies, which I'd be surprised if you haven't seen Marvel movies, especially Ant-Man, right? The quantum realm is weird, and that's actually not an exaggeration. That is the truth. The quantum realm is weird. Most things that we know about the world break down once you get to super, super small scales. Different forces take over. So Niels Bohr, anyone who is not shocked by quantum mechanics has not understood it. Schrodinger's is my favorite. I don't like it, and I am sorry I ever had anything to do with it. Schrodinger of Schrodinger's cat, which was a thought experiment. Nobody put a cat in a box with poison and then hypothesized about whether it was alive or not. And then Albert Einstein's quote, "God does not play dice with the universe." So it's not all random. There's underlying structure and forces at play. It's just trying to figure out what those forces are, where they are, and how to predict them. So the quantum mechanical model of the atom is foundational to modern chemistry. It forms the basis of the modern periodic table. It can guide our understanding of chemical bonding, which is what we'll do in chapter 10. And then some applications include semiconductor devices and design of new drugs. Very fundamental stuff. So we're first going to talk about light, which is electromagnetic radiation. You think you hear about electromagnetic radiation, and it might sound dangerous, but like These fluorescent lights are emitting electromagnetic radiation, like visible light is EM radiation. The cell phone signal, I don't know if you've ever thought about the fact that like your cell phone is able to send data to a tower through the walls way off in the distance somewhere and receive data.
Every episode of the first one.
And it's just like, but those, I mean, we'll talk about this more later, but the type of electromagnetic radiation is what determines whether or not it's dangerous. So light is not a form of matter. It's energy that travels through space, and it has a constant speed of 3 × 10⁸ meters per second, which is insanely fast. So I think it takes light 8 minutes to get from the sun, and the sun is like 100 million miles away, and it takes 8 minutes. So light is also weird because it has properties of both waves and particles. So an analogy for light is kind of like if you disturb the surface of water, waves are created, and those waves propagate out until they hit the edges of the water. Light is similar. It will continue to propagate, except it's electromagnetic radiation, and it actually exists in 2 different axes, the electronic axis and then the magnetic axis. So the waves carry energy as they move through the water. Right? You've been to the beach, you've been hit by a wave. Electromagnetic waves also carry energy, although a little bit different. So the wavelength, this is one of the important concepts to know. The wavelength of light is the distance between adjacent wave crests. So if you're measuring from peak to peak or crest to crest, that's the wavelength. How long is one wave? How long does it take to go from here, and then it goes down, and then it comes back up, right? And then this is constantly moving in a direction. So we can actually describe colors by their wavelength. So if you've ever thought like, oh, does blue look the same to me as it looks to somebody else? The answer is kind of yes. It's kind of depends on how your brain perceives it, but the same light creating the frequency for blue light is the light that's hitting your eyes is the same as hitting everybody else's eyes. Yeah, unless you're colorblind and your eyes are bad at picking it up.
If you're colorblind, what does it look like under like a black light, you know? Like, does it look just brown? You know how
Well, usually colorblindness is, so yeah, you're not able to perceive differences in colors, but you can still perceive differences in luminance.
Oh.
So whether something's brighter or darker. Yeah, that's another topic. So light carries a spectrum of, or white light carries a spectrum of wavelengths. So I should have brought a prism, but I didn't. So you can take a prism though, and it will split apart the different wavelengths of light. This is also how you get things like, right, the lights in here are very white lights. At home, you probably have more yellow lights, and that feels cozier. Those are different proportions of different colors, but still carrying most of the spectrum. And this is one of the weird things about light and colors. So a red shirt appears red because it's reflecting red. It's absorbing all of the other colors. And this is why white cars are more popular around here, because in the summer, the white light is reflecting all of the wavelengths, whereas a black car is absorbing all of the wavelengths. And so it's absorbing all of that energy and gets hot faster. So another property of light is its frequency. Let's talk about the wavelength. That's the distance between peaks of that wave. The frequency, I'm going to try and draw this. So if we have a wave, the frequency is how fast the peaks pass a certain point per unit time. So if you have your wave traveling through the air, and this is the sort of mark where we're measuring it. You know, if in 1 second, 100 peaks pass that point, that's a frequency of 100 hertz. So it's 100 waves per second. So you can imagine if you had a wave with a smaller wavelength, right? Light is always moving at the same speed. So if it's moving at the same speed, then a shorter wavelength means you get more peaks crossing that point per second. So if you have a shorter wavelength, you have a higher frequency. So they're inversely related. Oops. So we mentioned that light has properties of both particles and of waves. A light sort of particle or packet is called a photon. So it's a single energy packet of light. And then the amount of energy that's carried in one of these photons is determined by the wavelength of the light. And shorter wavelengths equal greater energy. So I think this is, or my analogy for this one is, it's like if somebody punched you, or have you guys seen Ip Man? No, it's like a martial arts, very, very good. It's on well, it used to be on Netflix. I don't know if it is now. Anyways, so it's like getting punched once, or getting punched like once per second, versus being punched 100 times per second. Right? The 100 punches is going to be more energy. Or if you want to use waves, if you're at the ocean and the waves are coming in really slow, then that's less energy than if the waves were just coming like one right after the other. So you can think of wavelength being short wavelengths means that you're getting hit by those photons more frequently, and that's higher energy. And so higher frequency, shorter wavelength is what determines the energy of a photon. So electromagnetic spectrum is a spectrum, and you can have any wavelength on this continuum. So from long wavelengths to short wavelengths, right? Long wavelength is low frequency, is low energy, and the longest wavelengths that are common are radio waves. So for AM radio, right, like it's like 500, 560, 600. I believe that's in megahertz or kilohertz. I don't remember. But then it might just be in hertz. So it's like 500, you're getting 500 waves per second. And then FM radio is a higher frequency. I believe those are in kilohertz. So like 101.1 is 101,000, well, 101,100 waves per second. And so you're getting that's the frequency, the literal number of waves per second that radio signal is delivering to your car, or that your car is picking up. And so because FM radio has so many more waves, they can transmit more data, which is why AM radio usually sounds like garbage, and FM radio is what we use for music. FM radio is also stereo, so you get left and right channel. AM radio is only mono channel. So there's no left and right balance. But moving up from radio waves, so that covers this very large portion, we get microwaves. So the frequencies actually used in your microwave are fairly long. The reason that they heat things up is because they resonate with the bonds in water molecules. And so they actually directly excite water molecules. The first use of microwaves, the first use of microwaves was as for radio transmissions, communicating with satellites, that kind of thing. And then somebody realized that birds would get cooked as they flew in front of the radio dishes, that you're using microwaves. And then at some point, scientists were working on cryogenics, right? So what if we could freeze somebody, like Futurama, and then they wake up 500 years in the future? Yeah. So they were researching this, and they realized, and they were starting with small animals. So they figured out that they could do this with hamsters. They could actually freeze a hamster, and with pretty good odds, thaw it later, and it would come back to life. It worked for hamsters. So they realized, though, that they were trying to like make as many hamsters survive as possible, obviously, but they realized that the more evenly you could thaw the hamster, the better its chances of survival were, and the less likely it was to come out with burns.
Put him in a microwave.
So they invented the first tabletop microwave to thaw hamsters. So the reason we have microwaves in our homes today is because they were trying to thaw hamsters.
So does that mean like in Austin Powers, like that's actually true? Because he's frozen, right?
In theory, it's hypothetically possible. The problem is when you get up to larger and larger animals, creatures, it's harder to thaw the entire person at the same time. And also there's just more damage. Yeah. So part of the problem with freezing is that it creates ice crystals and that ruptures cells.
I think they thought that because there's an insect that freezes in the winter and then it comes back to life in the summer or spring.
There's frogs, yeah.
Yeah.
Maybe probably insects too, but yeah, frogs also.
Disney Frozen is a park as well.
What? All right. Moving on.
It's funny though, when you drown cold water, you have a chance of surviving.
Oh yeah. Right, because as your body cools, it slows down. Are we going to talk about kinetics? We might talk about kinetics a little bit. That is related to kinetics, though. There's chemistry there, too. Okay, so moving on, though, infrared radiation is something that you feel all the time. So you get one of those space heaters. The reason that you can feel the heat from a space heater is because it's emitting infrared radiation. And that infrared radiation interacts with our skin and warms it up. And that's why if you're sitting around a campfire too, if you put anything between you and the fire, you immediately stop feeling the heat. Because what you're actually feeling is that infrared radiation. And then after infrared, we get into visible light. And this whole thing at the bottom is just expanded visible light. So we got on the lowest end, the lowest energy is red. And red, right, being right next to infrared, because infrared means below red. So a red is the longest wavelength. So it's this lambda here is wavelength. And then the highest energy is violet. And so on that end of the spectrum, we get UV light, right, ultraviolet. So it's above the energy of violet light and has even shorter wavelengths. And there's actually different types of ultraviolet light, UV light. I think it's UVA and UVB that cause sunburns. UVC can actually be used to irradiate things. I believe those are getting farther away from the visible light as you go ABC. So ultraviolet radiation is the first time where we start getting like damage directly from, or it damages human skin cells directly from the energy of electromagnetic radiation. So like your phones and everything too, those are using radio waves. Basically, these really low energy frequencies, which is why they don't affect us. They don't use microwaves, obviously, because then your pocket or your leg would get hot where your phone is. And then after ultraviolet radiation, which causes sunburns, you get X-rays, which of course in short bursts are useful for looking at bone fractures. Or if you've gotten a CT scan, that's just an advanced X-ray. So they're just taking a lot of slices, very detailed X-ray. And then after X-rays, we get gamma rays, which are the product of nuclear decay or nuclear bombs, or would be even produced by the sun also. Was that? Or the Hulk, yes. Yeah, don't go out and try and get dosed with a lot of gamma rays. You won't turn into the Hulk. It's not going to happen. So what you need to know from this is the relative positions, the relative energies of each of these types of light. So radio waves being the lowest energy, gamma rays being the highest energy, and then how everything sorts out in between.
But it's like the phone's is lower energy unless it's plugged into the wall with the charger, you got more energy. They say it's bad to sleep with like your phone on you when it's connected to when it's charging.
I don't know about, well, the frequencies that your phone is using don't change whether or not you plug it in or not. Yeah, that doesn't change. I think sleeping next to your phone is bad because you get notifications.
There was this girl on the news that her face blew up
Well, that is a good reason to not charge your phone next to your head.
Where does she get her phone from?
All right, so you need to know relative energies of different electromagnetic radiation. Be able to organize those by wavelength, frequency, and low or high energy. And so if you can remember the relationship, this is one of those things where if you remember the relationship between wavelength, frequency, and the amount of energy, you don't have to memorize all of these things individually. You memorize it for one. Right? Remember that either radio waves have the longest wavelength and that gamma rays have the shortest, and then you can figure out energy from there. Oh, right, I forgot that I always forget that these are written out here because I always go through them. So just as a quick recap, right, gamma rays have the shortest wavelength. They're the most energetic, produced by sun, stars, and certain unstable atomic nuclei on Earth. X-rays pass through many solid substances. Actually, gamma rays do also. They pass through pretty much everything. X-rays pass through a lot of things, but that's why you wear like the lead apron if you go to the dentist. Right? It doesn't pass through lead or other thicker materials. Can use X-ray or gamma rays actually for targeted tumor irradiation. There's a couple ways to do this actually. One is that you take a bunch of weak energy beams and you cross them. And so everywhere that the weak energy beam is passing through is a very low dose of radiation. But at the point where they all intersect, they're getting the overlapping radiation from all the beams to cause damage to the cancer cells. And especially for gamma rays, the damage is done by actually particles, the high energy particles hitting the DNA of the cancerous tumors and destroying the DNA. Because the problem with cancer is that it's a very fast replicating type of cell. So by disrupting the DNA, then they don't reproduce properly, and then hopefully they self-destruct like they were supposed to in the first place. The other way is that, and this is maybe getting a little bit into it, but the amount of energy from a gamma ray is mostly deposited when it stops. So as it's passing through something, it's not actually damaging anything unless it hits something. But the energy spikes right before it stops moving. So you can use this if you know the density of all the tissues where you're going to be targeting the tumor. You can essentially adjust the energy of the gamma ray to stop right inside the tumor where it would release all the energy. So those are the two ways to do that. Continuing down, ultraviolet light, right? UV light. It's what causes sunburns and suntans. It's less energetic than X-rays, but still has enough energy to damage skin cells. Visible light does not damage biological molecules. So that's why you don't get sunburns from lights inside. But it causes the molecules in your eyes to rearrange, allowing you to see colors and light. And fewer colors if you're colorblind. Infrared light is that light, again, comes off of hot objects. We can't see it, but you can feel it. It's also what lets night vision goggles work. They're just translating infrared signals into visible signals for your eyes, because everything emits infrared light. I think there's actually a picture here. Yeah. So in the regular photograph, infrared photograph. And this is not just a regular infrared photograph, but it's showing the temperatures of everything as well. So all of these blue areas are cooler, but the red areas are warmer. So like this dude's leg. The short-haired dog you can see the heat more than on the long-haired dog because the hair is trapping that heat inside.
Maybe that's how snakes can see.
So, and then microwaves, talked about microwaves, used at one point to thaw hamsters. And the reason that they were able to thaw hamsters is because the energy is efficiently absorbed by water. So every time the infrared light runs into a water molecule, that water molecule absorbs the energy, causing it to warm up. And then radio waves we use to transmit AM and FM radio signals. Also, you tell the slide's a little old, cellular telephones. Cell phones, television, other forms of communication, Wi-Fi, all fall into that range. Okay, so now we're going to take just visible colors and organize them in order of increasing wavelength, frequency, and energy per photon. If you remember Roy G. Biv, there's a great They Might Be Giants song about Roy G. Biv. It's a like leprechaun that lives at the end of the rainbow.
Is it the rainbow song?
Maybe?
It is for sure.
Yeah.
My
Okay.
daughter sings it in kindergarten.
Nice.
She's like, Mommy, who's Roy? And I was like, hello.
Yeah. That's going to be it. All right, so Roy G. Biv is in the order of energy, starting with the low energy red all the way up to violet. So here we're not doing all of those, but we're just doing green, red, and blue. So in terms of wavelength, which of these, red, green, or blue, has the shortest wavelength? Red is the highest wavelength. So blue is the lowest wavelength, shortest wavelength, because it's the highest energy. So blue has a shorter wavelength, and then we know that I said already that red is the highest, which means that green falls in between. How about frequency then? So just think about how frequency and wavelength are related. Yes. Yes. Because red has the lowest frequency, because the longest wavelength. So that means that there are fewer waves passing up any given point per unit time. What would be after red? It's green. And then blue. All right, so wavelength and frequency are inversely related. So wavelength is the distance between peaks. Frequency is the number of peaks that pass a point per second. So if you have peaks that are closer together, you have more of them passing per second, because they're always moving at the same speed. And then energy per photon. What's the lowest energy light, visible light? Yep. So red is going to be shorter than green. That's going to be, red is lower energy than green. It's lower energy than blue. So all three of these are related, right? Because you get more energy because you're getting hit by more waves. Alrighty, so that's the intro to wavelengths. So now we're going into the Bohr model of the atom. So the Bohr model, I guess we should start with these, what's on the slide. Neon atoms inside a glass tube. You can excite them with electricity, and then they emit light. So neon emits an orange light, and then you get mercury and hydrogen. I believe mercury is the blue here, and hydrogen is the pink. Oh yes, it's right there. Pink, blue. And so each element, if you can get it in a gaseous form, emits a different color of light. And so I believe that's why fluorescent lights, at least old ones, used mercury. Partly it increased the conductivity of the gas, so you can make longer tubes. But mercury also, I think, emits a pretty white light. So Bohr wanted to know why you could do this and why you got different amounts or different colors of light. Actually, if we go back to this, right, so then the energy, if we're using what we've just covered, the energy of the orange, which actually, wow, that's so dark on the screen. It's like bright orange on here. This is the difference in the colors. Okay, so that's orange. Just pretend that it's a very bright orange, but it's orange. So that means it's a lower energy light than like the blue or the blue of mercury. Oh yeah, mercury is blue. I should read the slides. Hydrogen is pink, right? So you're getting different energies of light emitted from these molecules or the atoms. And it gets even more interesting because if you take the light from a hydrogen lamp and you pass it through a prism, it splits the light, right, into its individual frequencies. So if we took light from these, we'd get a whole rainbow out on the other side of the prism. If you do this with a hydrogen lamp, you only get a few frequencies, a few wavelengths of light. And they're specific. So every time you do this with hydrogen, you get the same wavelengths. So white light spectrum, right, all of the colors. Hydrogen light spectrum, hard to see. This is called the emission spectrum. So each one is unique to each element. So there's one peak, there's one there, there's one here. There's actually two there, very dark. Just like one here. And that's for hydrogen. And then helium's is slightly different. And then when we move down to neon, all of a sudden we've got a lot of different lines, which hopefully you can see. It does look like the Netflix intro. Or there's those images where it's just like stripes of color and you have to guess what character it is. So these are unique to each type of element. So this is one of the ways that they look at exoplanets, so planets that are outside of our solar system, and try to determine what elements exist on that planet. Because they can analyze the frequencies of light that make it through the atmospheres of those planets as they pass in front of their star. So the light goes through the atmosphere, and then they've got distinctive gaps in the white light that the star produces. So the question then, of course, is why do they emit just certain frequencies of light? Why does hydrogen just emit one? Neon has a ton. Mercury even has a lot. So Bohr's model, Niels Bohr developed the Bohr model. And he came up with this idea that there are orbits. So these orbits are, as I could not draw, perfectly circular paths around the nucleus. Right, so we got our nucleus, which has protons and neutrons, and we have electrons. And according to the Bohr model, those electrons are particles themselves, and they're flying around in circles. Kind of like the Jimmy Neutron logo, if you ever watched that. At specific energies. So the distance from the nucleus and the energy of each Bohr orbit is fixed, or the fancy word for it is quantized. So there's a set amount of energy, and you can't exist in between two different levels of energy. And so the quantized orbitals are represented by quantum numbers. So we've got n equals 1, 2, and 3. So you can't have an electron kind of like a bouncy ball, if these were stairs maybe, right? It can bounce on this ledge, or it can bounce up to the higher ledge, but it cannot stop anywhere in between because it would just fall back down to the first level. Or if you're trying to walk up this ladder, climb up this ladder, you can't stand in between the first and the second rung. If you want to go higher, you have to go all the way up to that second rung. And then the distance between these orbitals for each atom is fixed.
How come the one between like 1 and 2 is huge and then it gets smaller?
It's because it takes more energy to go from 1 to 2. So this one is, this ladder is made, it's analogous to the energy levels around an atom. So then it's easier to go from, well, it's harder to go from the first orbit to the second orbit. But then as you get farther and farther away, part of that is because you're getting farther away from the nucleus. So remember, electrons are negatively charged, nucleus is positively charged. And kind of like magnets, if you get magnets really close, they snap together. But that attraction gets weaker really fast, right? It's only in that small distance that they're strong. So here, the electron is close to the nucleus, which would be the floor. And so it's really hard to make that first movement away from the nucleus. Once it gets farther away, though, now the attraction is weaker, so it's easier to make the next jump, and then even easier to make the next and the next. It's a good question. So in terms of these emission spectra, though, when the hydrogen atom absorbs that energy, it only has a single electron. And so that electron can be excited up to one of these different energy levels. And then as it relaxes, remember, energy is conserved. Can't destroy energy, can't create energy. So the energy comes into the electron jumps up to a higher energy orbit, and then it doesn't want to stay in that orbit because it's hard to stay in that orbit. It wants to have lower energy. So as it relaxes back down to a lower orbit, it emits light of a certain frequency depending on how far it jumped up. So if it absorbs a lot of energy, it'll jump up to a much higher orbital, like 3 or 4 or 5. If it absorbs a little bit of energy, then it'll jump up to 2. And then the amount of energy that comes out is determined by how far it relaxes. So the photon, that light that it emits, is also called a quantum. And the wavelength of that light depends on that relaxation. So for hydrogen, each of these transitions from 2 up to 3, or from 2 up to 4, or from 2 up to 5, and then back down again, emits different frequencies of light. So this jump from 3 down to 2 is a lower energy, longer wavelength, lower frequency light. And then if we're going from 4, then you get a blue-green. It's a smaller wavelength, higher frequency. And then the highest energy transition gives the violet light on the spectrum. So this was Bohr's theory. He said we can explain these lines by determining that the electron jumps to these different orbitals and then relaxes back down. And the reason it produces these specific lines is because there's only specific orbits that it can have. And of course, he did more than just like have a theory. He wrote down all kinds of math to try and explain this. And his model worked great, but only for hydrogen. If there were any more electrons involved, his model fell apart. So really, for a hydrogen atom, it's the only time you can think of it as an electron actually traveling on a single path. So this is the reason that the Bohr model was replaced, because it only worked for hydrogen. Although it did work perfectly for hydrogen, it didn't work for other things. And so the quantum mechanical model is what replaced it. Leave that there for a sec. So the key difference between the Bohr model and the quantum mechanical model, and this is the thing that you have to know, is that we replace orbits. We replace orbits with orbitals. And I'm just saying that weird to exaggerate that it's ALS. Orbitals, not orbits. So unlike the orbits, which are specific to defined paths, like the Earth traveling around the sun, or the moon traveling around the Earth. Orbitals are more like zones or regions where this electron can exist. And so it's not a single circular path, it's now a whole bubble in which the electron exists. And they're not, it's not like the electron is moving in paths, right? It's not moving in circles still within inside of this bubble. It's a statistical probability map of where that electron can be. So essentially like rolling a dice and saying, where's the electron going to be? And you roll a dice, and it's in this area, right, inside of this bubble, but it's over here. And for any moment, it can travel from one point to another point in the bubble without crossing the distance in between. Electrons are freaky. So they're no longer particles flying through space. They're waves, or wave-like particle-wave duality, existing around an electron. So I can describe this using an analogy with baseball. Right, so if you throw a baseball, very easy to trace the path of the baseball as it leaves the pitcher and goes to the catcher. Electrons, though, don't follow the same path every time. And you cannot trace its path from the pitcher to the catcher like you could a baseball. So every single time, even if it's thrown exactly the same way by like a pitching machine, the electron would land in different places. And so that's why we represent this with a probability map. So it has this wave-particle duality. So even though the electron is sort of, in this analogy, being thrown exactly the same way, there's a, I see, yeah. Zoom in on this. So in here, it's going to land in there 20% of the time. And if we expand our range out to here, that's going to contain 40% of all of the electrons thrown. And if you extend it all the way out to this outer bubble, or outer line, that's 70% of all electrons thrown will fall in there. 30% of the time, it's going to be outside of that. And again, it doesn't matter how it's thrown, every single time it'll land somewhere else. But if you do it enough, you can plot out the maps. And say most of the time it lands here. So as I mentioned, an orbital is a circular path, an orbit is a circular path, showing the electron's motion around the nucleus, and it's predictable, just like the baseball being thrown. And that was Bohr's model. He thought they had these predictable paths. The orbital, though, for the quantum mechanical model, is a probability map showing the relative likelihood of an electron being found at various locations. And it's completely unpredictable. The only thing you can predict is the area that it's going to be inside of. So for orbitals around a nucleus, we describe them with a number and a letter, kind of like an address. So the principal quantum number is n, just like we talked about with the, when we were talking about orbits. Principal quantum number is representing sort of the general area of where it is, the general energy level. And energy increases as n increases. So we've got these, you can think of them as like neighborhoods, or actually, you can think of them as like zip codes. Right, so the principal quantum number is like a zip code, and the higher the number, the farther away you are from the nucleus, which would be like the center of the city. Then we have also subshells, which specifies the shape of the orbital, and that's like the different neighborhood around the city. So we can be in the 2p, so that means our principal quantum number is 2. That tells us how far away we are from the center. And then the p tells us which sort of neighborhood that we're in, or the type of orbital. And they've got interesting shapes. So the 1s orbital is the lowest energy orbital. They're three-dimensional, so this is actually a sphere of points where the electron could be. So this is like taking a photograph of an electron every second for 10 minutes and then plotting them on a 3D plot. And then dot density represents the probability of finding an electron there. So if we look at this, we could draw lines like we had before and say that there's like different probabilities that exists inside of each of these regions. In the center, there's the highest density of dots, so this has the highest likelihood of being in that area. And then that sort of density of the dots decreases as we move out from the center. And then it really drops off, right, once you get outside of that. So we just know the electron is in there, don't know where. Don't know which direction it's moving. So the easiest way to think of orbitals is as geometric shapes. So the 1s orbital is a sphere. And the sphere represents a volume within which the electron is found 90% of the time. So in this bubble, 90% of the time, that's where the electron is. So the electron is expected to be outside of that shape 10% of the time. So there is some time that it spends outside of that bubble, and then it comes back. This is like me on vacation. 90% of the time, I'm at home and inside. 10% of the time, I have to get food. For the electron, we don't know where it goes, but it comes back. So that's the 1s. So the single electron of an undisturbed hydrogen atom, remember hydrogen only has one electron, at room temperature is in the 1s orbital. That's where it hangs out. And that's called the ground state, which is the lowest energy state. And electrons generally seek out the lowest energy orbital available. So they don't want to hang out in high energy orbitals. I don't want to hang out at high energy places. I like to stay in the lowest energy state possible. So the absorption of energy can cause the electron to jump to a higher energy orbital. So if something happens, it can be pushed up to a higher energy orbital, which is called an excited state, which is unstable. And so when it gets into this excited state, it wants to get back to the ground state. So all atoms have one ground state and then many excited states that are higher energy. Okay, so more about these and these orbitals, their energy levels. So the n equals 1 principal shell contains one subshell, s. So that's just the s neighborhood. It's like the inner city of the atom. The n equals 2 principal shell contains two subshells. So we have s, which is the sphere. S is a sphere, continues to be a sphere all the way up. The spheres just get bigger. The n equals 2, though, also has a p orbital, which we'll talk about. So 2s orbital is higher in energy and slightly larger than 1s. Because every time we increase that first number, higher and higher energy. The 2p subshell, so once you got 1s, we go 2s, then we go 2p, is shaped differently, and it's called a dumbbell shape, because it kind of looks like a dumbbell. And each of these three orbitals has the same amount of energy. So it takes the same amount of energy to be in each of these. And they each have different orientations and do not overlap. So even though they look like they all have a point in the center, that point in the center is the nucleus, and the electrons don't go to the nucleus. So you have this one on the x-axis, this one is on the y-axis. You can kind of think of that as going in and out of the projector screen there. And then this one is on the z-axis, so perfectly vertical. So you've got two that are forming an X, and then one that goes up and down through the center of those. Those are the p orbitals. So the number of subshells for any given principal shell is equal to n. So n equals 1, we have one subshell, 1s. N equals 2, we have s and p. When you get up to n equals 3, you now have s, p, and d. And then you get to 4, you get S, P, D, and F. To my knowledge, there's nothing after F.
Does the S and the P and the D and the F stand for something? That's why you chose that letter?
That's a good question, and I don't know if there is.
Most likely there is.
Huh?
I said most likely there is.
There's got to be some reason, yeah.
No.
You can think of S's for sphere.
Just picked it up out of my hat and was like,
Yeah.
Imagine it has to do with the either the shapes or it's from a different language. So the N equals 3 principal shell contains 3 subshells. So you have S, P, and D. S and the P subshells contain 3s and 3p orbitals. So we've gone from 1s to 2s. Now we have 2p, and then we have 3s, 3p, and 3d. And the 3s and 3p are similar in shape, but slightly larger than the ones below them, right? The 2s and 2p. And then the d subshell contains 5d orbitals. And those 5d orbitals are kind of like the dumbbell shape, but now each of them has 2 dumbbells. So there's one that's in between the y and z axis. It's in between the x and y axis, and then in between the x and z axis. And you can kind of think of this also like, this is going to sound like a weird analogy at first, but bear with me. If you're packing a suitcase, right, at first you have a lot of space. So that's the 1s orbital. We're packing electrons around this atom. So the 1s orbital has a lot of space. It's easy to just put stuff in there, takes up most of the middle of the suitcase. And then you start getting to like the smaller things. You're like, well, I still got to put stuff in here. So you're fitting, the p orbitals fit around the gaps of the s orbital. She's like, well, I used up all that space, so we're going to pack them into these corners. The d orbital is where you're finally like just looking for every single tiny spot. That's where you're shoving socks into shoes. And you're like, I can pack these things in all of the little tiny corners. Is kind of what's happening here. So none of these orbitals really overlap with each other. They're finding extra little spaces around the atom. And so that's why they get more and more complex as we keep going. My favorite orbital is the dz squared, because it's a dumbbell with a donut. It looks like a double-sided pacifier. This one, though, is weird because this donut is not attached to the dumbbells, but the electron can be either in the dumbbell or it can be in the donut, and it does not have to cross the space in between. So remember, these are not paths that the electrons are taking. They're not traveling in figure eights. They're just appearing and disappearing within these orbitals. They're just spaces where the electron is most likely to be. Perfect. So the electron configuration is how we represent all of the electrons. Because we've got all these orbitals now. There's all these places where we can fit electrons. But how do we describe where they are? So we use electron configurations to describe the locations of the electrons. An electron configuration, occupation of orbitals. And we start with the lowest energy orbital first, which is 1s. And then as we add more electrons, we add them in increasing order of energy. So this is hydrogen's ground state electron configuration. So we have hydrogen, so it has 1 electron, so we put that in the 1s orbital. And I'm going to try and show you how to use the periodic table to make this really easy. All right. Another way we can represent this is with orbital diagrams. So an orbital diagram is like an electron configuration, but it's showing us the electron specifically. Now, electrons have this quantum mechanical property called spin. And so this is a little like half up arrow. That means it's an up spin electron. And then you can also have a down spin electron. So for helium, we would have a box. This would be still the 1s orbital. and then it would have one upspin electron and one downspin electron. So we can show exactly where the electrons are and how they're fitting into each of the orbitals. So I told you about spin, but the Pauli exclusion principle just states that orbitals can hold no more than 2 electrons, and they have to have opposing spins. So if you have one upspin electron, the other electron has to be downspin. Yes, write the electron configurations for orbital diagrams for helium and lithium. Okay, so helium. The electron configuration for helium, you can actually get straight off the periodic table. So looking at the periodic table, right, the first row is n equals 1. That's the first principal quantum shell. So n equals 1 is the first row. So that means that we only have one orbital, and our first and lowest energy orbital is 1s. So helium is 1s. And then the number of elements in the row, or the element's position in the row, tells you how many electrons it has. So helium is the second element in the first row. So it has 2 electrons. So for its electron configuration, we say it's got a 1s orbital, and in that 1s orbital, 2 electrons. And then the orbital diagram will have one box, because again, helium's in the first row, only has 2 electrons, so it's going to be 1s. And then we put 2 electrons in there. One of them is a half arrow up, the other one is a half arrow down.
Because it has 2 electrons.
Because it has 2 electrons, yeah. And because the Pauli exclusion principle says they have to have opposite spins. And it doesn't matter if the first one's up and the second one's down, or if the first one's down and the second one's up, they just have to be opposite. I always just write the first one is up. Okay, so that's helium. Now lithium, right? Lithium is in the second row of the periodic table, and it's the first element in that row. So every element is going to have all of the electrons of every element before it. So for lithium, it's going to has also helium and hydrogen before it. So how many electrons does lithium have? 3. So if we start writing out our electron configuration, we're going to have 1s. But 1s only has 1 orbital, so we can only put 2 electrons there. So it's 1s2. And then what's the next orbital? Almost. It's in the second row. We can only put 2 electrons here. So in the second row, we move from 1s to 2s. And so we've already placed 2 of lithium's 3 electrons. So we only have 1 more electron to place in the 2s orbital. So then an orbital diagram will have a box for each orbital. And so in our 1s orbital, how many electrons are there? 2 electrons. Because we had 1s2. And in the 2s orbital, how many electrons are there? Just 1. Yeah, so the number in front tells us what the energy level is, what the principal quantum shell is, the overall energy level. And then the number of electrons is determined by that superscript. I think we're going to get more examples, because I definitely want to do more complicated ones. But Those are some of the simpler ones. So in multi-electron atoms, so the more electrons that you add in here, the more orbitals that you have to start filling up. And they always fill from the lowest energy to the highest energy. And these are the relative energy levels of these orbitals. So it goes 1s, then 2s, and then we get 2p orbitals, and there's 3 of those. And then we get 3s, and then 3p, and then 4s. And then after 3s, or 4s, the order gets a little bit weird. Okay, so for carbon, we write out an electron configuration. So how many total electrons will carbon have? 6. All right, so it's going to have all of the electrons of all of the elements before it, plus its own one, plus one last electron to make it carbon. Stumbled over that. Okay, so we can start again with 1s. You always start with 1s, unless you use a shortcut, and we'll talk about shortcuts later. So 1s, 2.
We always start with 1s?
Mm-hmm. Unless you use a shortcut. We haven't talked about shortcuts yet. But the lowest energy orbital is 1s. So every single element on the periodic table is going to have a 1s orbital. And you got to put the electrons there first, and then once that's full, then you move to the next one. And once that's full, you move to the next one. And so you're always filling them up from the bottom. So what's the next orbital? 2s. So, right, we did the electron configuration for lithium, and that was 2s1. So if we do lithium and beryllium, it'll be 2s2. And of course, we can only have 2 electrons there also. So now we have two types of orbitals once we get to n equals 2. So now instead of 2s, we also have 2p. So now we've already filled in 4 electrons. How many electrons will carbon have in the 2p orbital? Yeah, right? All the electrons that are left. And so those have to be written as superscripts there. So for an orbital diagram, then, we're going to have all of the same orbitals as our electron configuration. But now's the first time that we're getting an orbital, or we're getting a subshell that has multiple orbitals. And so we can use our electron configuration as a guide to fill in these boxes. So 1s is going to get 2 electrons, opposite spins. 2s is also going to get 2 electrons. And then 2p, we have 2 electrons left. And so this is Hund's rule. You fill them in with 1 electron at a time first. And then if we run out of space, like we did with the 1s and the 2s, then you pair them up. Right? If we can't do 1 at a time, then we'll pair them.
When it's 2p, you always have the 3 boxes?
Mm-hmm. So 2p had the 3 dumbbell shapes. So there's 3 orbitals in that subshell.
So as long as the exponents equal the number of electrons, that's how we find our answer?
For the orbital diagram?
Yeah.
Yeah, the orbital diagram can help you fill out the electron configuration, tells you the number of electrons in each subshell. Mm-hmm.
You know how the carbon?
Mm-hmm.
It has a 6 already up there. Can we just use that instead of having to count 1, 2, 3?
Mm-hmm. Yeah, in the ground state, every element is going to have the same number of electrons as it does protons. Now there's, I guess we'll come back to that. Yeah. All right, so this is the quantum hotel.
Are we doing the Hans rule, or we already did it?
Oh yeah, sorry. I mentioned Hund's rule briefly. We're gonna talk about it more in the quantum hotel. But when you're filling orbitals of equal energy, you fill them singly first with parallel spins. So here I filled these separately instead of putting them together, and then they both have up spins.
You could have done, can you put one up spin and one down spin? Does it matter?
No, they have to be parallel spins. So they'll all spin in the same direction first, and then when you add in more electrons, they'll go downspin. I guess we can come back to this. And I'll talk about this first before we move on. On the periodic table, we've talked about like groups. Those are the numbers, like vertical columns, right? Group 1, group 2. There are also blocks. So everything in group 1 and group 2 is going to have its valence electron, which we haven't quite gotten to yet. Last electron is going to be in an s orbital. Right, so if we did the electron configuration for lithium, right, its last electron was, go back up to it, right, 2s1. Beryllium would also have its last electron in s. So that's called the s block. So all of those elements with that last electron, the electron configurations are going to end in that s block, or in an s orbital. On the right side, from boron, group 13 up to 18, that's called the p block. And all of those elements have their last electron in a p orbital. And then in the middle, from 3 to 12, groups 3 to 12, that's the d block, and they have their last electron in a d orbital. And so rather than counting these out and going one at a time, you could look at something like carbon and say carbon's got, well, hydrogen, helium, so that's going to be 1s. Lithium and beryllium are both in the s block, so it's going to be 2s2. And then carbon is the second element. I'll go back down to carbon. Carbon's the second element in the p block, so it has 2 electrons in its p orbitals. If we did the electron configuration for nitrogen, right, it's the third element, so 13, 14, 15, third element in the p block. So it's going to have 3 electrons in its p orbitals. So you can also use that as a shortcut for writing down these electron configurations. Practice. Practice, and we're going to do more of these. Righty.